Hey there, deep diver. Ready to tackle some serious math today.
I think we are.
We're going to plunge headfirst into the world of Latin squares.
Oh, yeah.
And this paper that's making waves, almost every Latin square has a decomposition into transversals.
Right.
Buckle up, because this one's a brain bender.
You're not kidding. This paper tackles a problem that's been puzzling mathematicians for centuries, going all the way back to Euler.
Okay, so before we get lost in the weeds, let's remind ourselves what we're dealing with.
Yeah.
We have this research paper, and it's all about proving something pretty surprising about Latin squares.
It is.
But first things first, what exactly is a Latin square?
Well, imagine a Sudoku puzzle. You know that grid where you have to place numbers so they only appear once in each row column and smaller square?
Ah, Sudoku, the bane of my existence. Okay, so that's a Latin square.
It's a type of Latin square. More formally, a Latin square of order n is an nxn array. So a grid with n rows and n columns filled with n different symbols. And just like in Sudoku, each symbol appears exactly once in each row and each column.
Okay, so instead of just numbers, we could have letters, colors, or even emojis, as long as they follow that rule.
Precisely. Now, where it gets interesting is with this concept of transversals.
Okay.
Imagine selecting n cells from the square one from each row and column. But here's the catch. No two cells can contain the same symbol. That's a transversal.
So it's like a special diagonal where all the symbols are different. I'm starting to see why this would be a tricky thing to find.
It can be, especially when you start dealing with larger squares. And that brings us to Euler's famous conjecture.
Right.
He was looking at Latin squares, where the order n is congruent to 2 modulo 4. That means when you divide m by 4, you get a remainder of 2.
Right, so we're talking about squares of order 2, 6, 10, and so on.
Exactly. Euler conjectured that these particular types of Latin squares don't have any transversals.
Really? And this conjecture stood for over 100 years.
It did. It was a major puzzle in combinatorics. Eventually, it was disproven.
Wow.
But this paper we're diving into takes things a step further. They show that not only do most of these squares have transversals, but you can actually break them down entirely into a collection of transversals.
Wow, so you could decompose the whole square
Yeah.
using these special diagonals. That's pretty mind-blowing.
It is. And the way they prove it is really ingenious. They connect Latin squares to something you might not expect. Graph theory.
Graph theory. So we were talking about those diagrams with dots and lines.
Yeah.
How do those relate to Latin squares?
Here's how they do it. They use a special type of graph called an optimally colored complete bipartite graph.
Okay, let's unpack that. What's a bipartite graph again? I vaguely remember something about two sets of vertices.
You're on the right track. A bipartite graph has 2 sets of vertices. Let's call them set A and set B. Every vertex in set A is connected by an edge to every vertex in set B, but there are no connections within the sets themselves.
So like two teams, and everyone on one team is connected to everyone on the other team.
Yeah.
But there are no connections within the same team.
Perfect analogy. Now, complete bipartite means every possible connection between the 2 sets is made.
Okay, so we've got our 2 teams fully connected. What about this optimally colored business?
That's where it gets really interesting. In an optimally colored bipartite graph, each edge gets a different color, and you use the minimum number of colors possible so that no 2 edges connected to the same vertex have the same color.
I see. So it's like a very organized coloring party. I think I'm starting to see the connection to Latin squares here. Each team could represent the rows or columns of the Latin square, and the colors could represent the symbols.
You got it. Each set of vertices in the bipartite graph represents either the rows or columns of our Latin square. The edges, which connect every vertex in one set to every vertex in the other set, represent the cells in the square. And crucially, the colors of those edges represent the symbols within the cells.
So by creating this bipartite graph, they've essentially turned our Latin square into a visual network of connections and colors.
Exactly. And what's brilliant about this is that it allows them to study transversals in the Latin square by looking at something called rainbow matchings in the corresponding graph.
Rainbow matchings. Sounds intriguing.
Think of it like this. A matching in a graph is a set of edges where no 2 edges share a vertex. It's like pairing up people in those 2 teams we talked about, ensuring everyone has only one partner.
Okay, so we've paired up our teams. What makes it a rainbow matching?
In a rainbow matching, every edge in the matching has a different color. So going back to our analogy, it's like ensuring that every pair of people holding hands has a different colored glove.
I love that analogy. So they've translated the problem of finding transversals in a Latin square to finding these colorful pairings in a graph. Very clever.
It is. It's a brilliant way to bring in the tools and techniques of graph theory to tackle this old combinatorics problem.
Yeah.
And the beauty of mathematics is that seemingly disparate fields can often be connected in surprising and powerful ways.
Absolutely. I'm eager to dive deeper into how they actually use this graph theory connection to prove their result.
Well, that's where things get even more fascinating. They introduce a technique called the switching method to analyze what happens in random Latin squares.
Okay.
But before we get to that, let's take a closer look at exactly what they're trying to prove. Their main result is that almost all Latin squares can be decomposed into transversals.
Right.
What does that actually mean mathematically?
That's a great point. Let's make sure we're all crystal clear on what this decomposition entails. So we know a Latin square has n rows, n columns, and n symbols. And a transversal is a selection of n cells, one from each row and column, with no repeated symbols. What the paper claims is that for most Latin squares, we can find a collection of these transversals that together use up all the cells in the square. Is that right?
Precisely. It's like taking a jigsaw puzzle and finding a way to perfectly assemble it using only these special diagonal pieces, the transversals.
Okay.
And the paper's breakthrough is proving that this is possible for almost every Latin square out there.
Okay, now that we've clarified the goal, I'm ready to hear about how they actually go about proving it. Let's hear about this switching method you mentioned.
Okay, imagine our optimally colored, complete bipartite graph.
Uh-huh.
Remember, it represents our Latin square with vertices as rows and columns, edges as cells, and colors as symbols.
Right, I've got that picture in mind.
Now, the switching method involves making small, controlled changes to this graph. They essentially swap around a few edges while keeping the overall structure intact.
So they're carefully tweaking the connections in the graph.
Exactly, but they don't do this randomly.
Okay.
They're looking at how these switchings affect the number of rainbow matchings in the graph. Remember, rainbow matchings correspond to those special transversals in our original Latin square?
So they're making these controlled changes to the graph, and by observing how those changes impact the rainbow matchings, they're learning something about transversals in the Latin square.
Precisely. And the really clever part is that they use this switching method along with some heavy-duty probabilistic arguments to show that in a randomly generated Latin square, it's incredibly likely to have a full set of transversals.
So by analyzing how these switchings work in a random setting, they're able to draw conclusions about the structure of almost all Latin squares. It's like looking at a jumbled up mess and finding hidden patterns within the chaos.
It is. It's a powerful demonstration of how probabilistic methods can be used to uncover deep truths about seemingly deterministic objects. But the paper doesn't stop there. They also hint at connections to something called resolvable designs.
Resolvable designs. This is the first time we're hearing about those.
Yeah.
Tell me more.
Think of a resolvable design as a way to arrange objects into groups with specific properties. What's fascinating is that this paper suggests a link between their findings about transversal decomposition and the resolvability of certain types of designs. It's like they've opened a door to a whole new area of research.
So by cracking this puzzle about Latin squares, they might have stumbled upon a deeper connection to other areas of combinatorics. That's pretty remarkable.
It is. And it speaks to the beauty of mathematics, where a single problem can often lead to a cascade of new insights and connections.
I'm already blown away, and we've only just scratched the surface.
Yeah.
I can't wait to dig into the specifics of their proof.
Me neither. Let's get ready to roll up our sleeves and dive into the nitty-gritty details of how they pulled this off. All right, so we've set the stage, we know the problem, and we have a sense of the overall strategy. Let's get into the heart of their proof, which is a beautiful blend of probabilistic methods and clever deterministic constructions.
I'm ready. You mentioned earlier that the proof has three main parts. Where do we even begin with something this complex?
Well, the authors start by setting up what they call an absorption schematic, which sounds intimidating, but it's actually a brilliant way to guide the later steps of the proof. Think of it as a carefully crafted blueprint that lays out how they will use the switching method to eventually create those perfect rainbow matchings we talked about.
Okay, so it's like a roadmap for the rest of the proof. They're not just randomly switching edges. They have a plan.
Right.
But how do they create this absorption schematic? It still sounds pretty abstract to me.
You're right. It is a bit abstract at this point. To make it more concrete, let's go back to our bipartite graph, which represents our Latin square. Remember, the vertices are the rows and columns, the edges are the cells, and the colors are the symbols.
Got it, our colorful network.
The absorption schematic involves partitioning the vertices of this graph into carefully chosen subsets. These subsets are designed to have certain properties that will be crucial later on when they apply the switching method.
So they're strategically dividing the rows and columns of the Latin square into groups. What's the purpose of that?
It's all about control and balance.
Okay.
They want to ensure that when they start switching edges, they have enough resources, vertices, and edges available in each subset to make the necessary manipulations. It's like a general carefully deploying troops to different battlefronts, making sure each unit has enough soldiers and supplies to carry out its mission.
That's a helpful analogy. So by dividing the vertices into these subsets, they're ensuring that no single part of the graph gets overloaded during the switching process.
Exactly. It's a delicate balancing act, and they use probabilistic calculations to ensure that the sizes of these subsets fall within certain ranges that make the later steps of the proof work.
Okay, so we have these carefully chosen subsets of vertices. What else is important about this absorption schematic?
Another key property is the connectivity between these subsets.
Okay.
Remember, the switching method involves swapping edges.
Right.
To do this effectively, you need to make sure there are enough potential switching paths between the different subsets. It's like making sure there are enough roads and bridges connecting those different battlefronts in our analogy.
Right, so it's not just about having enough resources in each subset, but also about ensuring those resources can be moved around and shared when needed.
Exactly. The absorption schematic is all about carefully setting up the infrastructure for the switching method to work its magic.
This is starting to sound incredibly intricate. It seems like they're building a very elaborate network with these subsets and connections. How do they actually go about creating this schematic in a way that guarantees the properties they need?
That's where it gets really technical.
Okay.
They utilize a two-step process involving what they call auxiliary graphs. Now, these aren't the main bipartite graph we've been talking about,
Right.
but rather additional graphs that serve as templates for selecting where to place certain crucial structures within the main graph.
Hold on, more graphs. I'm starting to see why this paper is considered such a breakthrough.
Yeah.
But I'm also getting a little lost. Can you break down how these auxiliary graphs help them create the absorption schematic?
Absolutely. Let's start with the first auxiliary graph. This graph is carefully constructed to be sparse, but well-connected. Sparse means it doesn't have too many edges,
Okay.
but well-connected means you can still find a path between any two vertices.
Okay. Sparse but well connected. What's the purpose of creating this first auxiliary graph?
Remember how we talked about needing to ensure connectivity between the subsets in our main graph?
Uh-huh.
Well, instead of trying to create direct connections between every single pair of vertices, which would be very messy and inefficient,
Right.
they use this first auxiliary graph as a guide.
So it's like a simplified map of the connections they want to create in the main graph.
Exactly. The edges in this first auxiliary graph represent pairs of vertices in the main graph that they will focus on connecting. It's a way to strategically prioritize which connections are most important for the later stages of the proof.
That makes sense. So it's all about being strategic and efficient. But you mentioned there's a second auxiliary graph. What role does that play?
The second auxiliary graph is built upon the first and serves to refine the structure even further. Remember those paths we talked about between any two vertices in the first auxiliary graph? Well, the second auxiliary graph is designed to ensure that many of those paths are edge disjoint, meaning they don't share any edges with each other.
Why is that important?
Think of it like a transportation network. You want multiple routes between cities so that if one route gets blocked, you still have alternative ways to get around.
Yep.
Similarly, in the graph, having edge disjoint paths provides flexibility and robustness. It means that if one path becomes unusable during the switching process, there are other paths available that won't be affected.
So it's like building in redundancy to make the system more resilient.
Precisely. And this property becomes crucial later on when they actually use these paths to manipulate the matchings. It helps to prevent conflicts and ensures that the switching process can proceed smoothly.
This is all starting to sound incredibly complex, but also incredibly clever. I'm starting to appreciate the level of planning and foresight that went into designing this absorption schematic.
It's truly impressive, and all of this meticulous setup is done to ensure that they can control certain key properties of the graph that are essential for the later stages of the proof. Okay. For example, they want to ensure things like low codegrees in these auxiliary graphs, which basically means controlling how often certain combinations of vertices and edges appear together.
So it's all about carefully setting the stage for the main act, which is the switching method.
Exactly. The absorption schematic with its switchers, auxiliary graphs, and carefully chosen subsets might seem complex, but it's a masterful way to lay the groundwork for a much smoother and more controlled application of the switching method in Part B.
I'm getting a sense that this paper is all about balancing complexity and control. They're dealing with a very complex object, a random Latin square.
Right.
But they're using these incredibly clever techniques to impose a level of structure and control that allows them to prove something remarkable.
You've hit the nail on the head. It's a beautiful testament to the power of strategic thinking in mathematical proofs.
I'm eager to hear how all of this comes together when they apply the semi-random method in Part B. But before we move on, I have one more question about these auxiliary graphs. You mentioned they're used to select where to place certain structures in the main graph. What exactly are these structures and how do they help?
That's a great question. Remember how we talked about switchers earlier?
Uh-huh.
Those special pre-placed mechanisms that allow them to rearrange edges in the main graph?
Right.
Well, the auxiliary graphs are used to determine precisely where these switchers should be placed.
So they're not just randomly inserting switchers into the graph, they're using these auxiliary graphs as a guide.
Exactly. It's all about being strategic. They want to place the switchers in a way that maximizes their effectiveness and minimizes potential conflicts during the switching process. The auxiliary graphs provide a framework for making those decisions in a careful and controlled manner.
This is starting to feel like a very elaborate game of chess, where they're thinking many moves ahead to anticipate potential problems and set themselves up for success.
That's a great analogy.
Yeah.
And like a skilled chess player, they're using their deep understanding of the underlying structure to outmaneuver the inherent randomness of the problem.
Okay, I think I'm starting to wrap my head around this absorption schematic. It's a lot to take in, but I see how it sets the stage for the rest of the proof. Are we ready to move on to Part B and see how they actually use this schematic to find those near-perfect rainbow matchings?
Absolutely. Let's delve into the heart of the action and explore how the semi-random method comes into play.
Okay, I think I'm following. So far we've got our Latin square.
Yeah.
We've transformed it into this bipartite graph, and they've cleverly created this absorption schematic with all its bells and whistles. What happens next? How does this semi-random method actually work?
This is where things get really dynamic. The semi-random method is like a carefully choreographed dance between randomness and control.
Okay.
It's an iterative process where they gradually build up the desired matchings over several steps.
So they're not finding these near-perfect rainbow matchings all at once. It's more like building a house brick by brick.
Exactly. They start with a small set of edges, and then in each iteration, they carefully add more edges to the matchings guided by the structure laid out in the absorption schematic.
So it's a step-by-step process, but it's not completely random, right? The absorption schematic is acting like a set of rules or constraints guiding the construction of the matchings.
Precisely. And a key to this process is ensuring that the matchings they build are not only near perfect, meaning they cover almost all the vertices, but also balanced.
Balanced. What does that mean in this context?
Remember those subsets of vertices we talked about earlier? The ones they carefully created in the absorption schematic? Balance means making sure that each matching they build uses roughly the same number of vertices from each of those subsets.
Oh, I see. So it's like making sure they're distributing the resources evenly. If one matching used up too many vertices from one subset, it might leave others with too few to work with later on.
You've got it. Maintaining this balance throughout the semi-random process is absolutely crucial. It ensures that all of the matchings have the potential to be completed into perfect matchings in the final stage of the proof.
Okay, so they're carefully adding edges in each iteration, guided by the absorption schematic and making sure to keep things balanced along the way. This semi-random method sounds incredibly intricate. I can only imagine the level of detail and precision involved in designing and analyzing each step.
You're right. It's a highly technical process. The authors had to carefully design the iterative steps, making sure each iteration maintained the balance and structural properties needed for the proof to work. They also had to prove that each step could be carried out successfully with high probability, meaning that the chances of things going wrong were extremely low.
So it's not just about having a good idea, it's about proving that the idea actually works in a rigorous mathematical sense. That must have involved some pretty heavy-duty probabilistic arguments.
It did. They used a variety of powerful tools from probability theory, including concentration inequalities and martingale arguments, to show that their semi-random process behaved as expected with high probability. It's a beautiful demonstration of how probability can be used to create and analyze complex structures.
It's mind-blowing to think that randomness can be harnessed in such a precise and controlled way. It's like they're taming chaos to achieve a specific goal.
It is. And what's remarkable is that they're not just dealing with any kind of randomness, they're working with a random Latin square, which at first glance seems like a completely chaotic object.
Right.
But by using these clever techniques, they're able to impose a level of order and structure that allows them to uncover these hidden properties.
This is truly groundbreaking work. Okay, so they've used the semi-random method to create these near-perfect balanced matchings. What happens in the final stage of the proof? How do they go from these near-perfect matchings to a complete decomposition of the Latin square?
Now we enter the final act, part C of the proof, where all the careful planning and preparation in the previous parts come to fruition. Remember those switchers we talked about earlier?
Yes.
Those special structures strategically placed in the graph according to the absorption schematic.
Right.
This is where they come into play.
Ah, so they finally get to use those tools they've been so carefully crafting. But how do these switchers help them go from almost there to a complete solution?
The goal now is to connect those near-perfect matchings using the switchers and the paths between them to create a set of perfect rainbow matchings that together decompose the entire graph.
So they're using the swishers to link up those almost complete matchings, filling in the gaps and ensuring that every vertex and every color is included in the final decomposition. It sounds like a very delicate and intricate process.
It is. It's like the grand finale of a fireworks show where each explosion has to be timed perfectly to create the desired effect. Well, the authors had to meticulously analyze the mashings produced by the semi-random method, identifying exactly which vertices and colors still needed to be incorporated into the final decomposition. Then, using those switchers and paths as their tools, they carefully manipulate the edges to fill in the missing pieces.
I imagine this final stage is prone to creating conflicts. What if a switcher they need to use is already being used by another matching?
Yeah.
Or what if two switchers are too close together and interfere with each other?
Those are great questions. And the authors anticipated those kinds of conflicts. That's why they put so much effort into designing the absorption schematic so meticulously. Remember how the second auxiliary graph ensured that many of the paths between switchers were edge disjoint, meaning they didn't share any edges? That property plays a crucial role in minimizing conflicts during this final refinement stage.
Ah, I see. So their careful planning in the earlier parts of the proof is now paying off, helping them navigate the complexities of this final step. It's like they've set up a system where the different parts work harmoniously to achieve the overall goal.
Exactly. They've essentially created a well-oiled machine that can take a seemingly chaotic object, a random Latin square, and extract from it a beautiful underlying structure. It's a testament to the power of human ingenuity and the elegance of mathematical reasoning.
This entire proof strategy is absolutely breathtaking. They've combined powerful probabilistic methods with clever deterministic constructions, meticulously analyzing each step to ensure a successful outcome. It's a true tour de force.
I agree. Their work is not only a major breakthrough in combinatorics, but it also highlights the power of interdisciplinary thinking. By bringing together ideas from graph theory, probability, and design theory, they've opened up new avenues for research and shed light on connections that were previously hidden.
It's a reminder that sometimes the most profound discoveries come from exploring the unexpected connections between seemingly disparate fields.
And it underscores the importance of curiosity-driven research. Who would have thought that a problem about Latin squares, these seemingly simple objects, would lead to such deep and far-reaching insights?
This has been an incredible journey. We started with Latin squares and ended up exploring a world of bipartite graphs, rainbow matchings, absorption schematics, and the semi-random method. It's been a true deep dive into the heart of cutting-edge mathematical research.
It has. And what's so exciting is that this is just the beginning. The author's work has opened up a whole new set of questions and possibilities. Who knows what other mysteries lie hidden within the world of Latin squares and related structures?
Exactly. It's a reminder that there's always more to explore, more to discover. So, dear deep diver, keep those mathematical gears turning. You never know what incredible insights you might uncover. Until next time. Welcome back to the deep dive. This time, we're going deep into combinatorics, specifically Latin squares.
Oh, very cool.
You know, those grid-like puzzles like Sudoku.
Yeah.
but with a lot more mathematical depth to them. We've got a research paper here, and the title is, well, get this, almost every Latin square has a decomposition into transversals.
That's a mouthful.
It is. And let me tell you,
Yeah.
it's pretty groundbreaking stuff.
Absolutely. It really changes how we think about Latin squares, yeah.
So before we dive into all the nitty-gritty, can we just take a step back?
Sure.
For those who might not be as familiar, what exactly are we talking about when we say Latin square?
Well, imagine you have a square grid, right?
Okay.
It could be 3 by 3, 5 by 5, really any size, n by n.
Right.
And you fill that grid with n different symbols. So it could be numbers, letters, colors, whatever you choose. But the rule is each symbol can only appear once in each row and once in each column.
Ah, okay, so that's the key.
That's the key, yeah.
So kind of like Sudoku, where you've got those numbers 1 through 9, and they can only appear once in each row, column, and those little 3 by 3 blocks.
Precisely. Sudoku is like a very specific type of Latin square.
Okay.
But Latin squares in general are much more broad.
Got it.
They don't have to be 9 by 9, and they don't need those smaller blocks.
Right, so this research, it's looking at that bigger picture, regardless of the specific content of the square.
Exactly.
Okay, so now let's get to the heart of this research, those transversals.
Right.
Can you break down what that concept means?
Sure. Imagine you're looking at your Latin square, and you want to pick out n cells from it.
Okay.
One from each row and one from each column. But here's the catch. No two cells you pick can have the same symbol.
Ooh, so it's like a diagonal slice through the square, but not necessarily a perfectly straight line?
Exactly. It's like a diagonal, but it can kind of zigzag a bit, and that's what we call a transversal.
Okay, it's starting to see the picture. So the big question here is, can you always slice up a Latin square into these transversal patterns?
Precisely. And for a very long time, mathematicians actually thought the answer was no, at least for certain kinds of Latin squares.
Oh, interesting. Why is that?
Well, this belief came from a conjecture made by Leonhard Euler way back in the 18th century.
Like Euler? Like the EI plus 1 is 0 Euler?
The one and only. He was, well, a genius, to say the least.
For sure.
And he had this hunch about Latin squares, specifically those with sides that are a multiple of 4 plus 2.
So like a 6 by 6 square or a 10 by 10.
Exactly. He basically said these squares couldn't be fully broken down into transversals.
And now this new research is saying he was wrong. That's a pretty big deal.
Yeah, it's a pretty big deal. It's a big shift in our understanding, for sure. For over 200 years, his conjecture was kind of just accepted as fact. Then in 2020, there was a mathematician, Matthew Kwan.
Okay.
He made a major breakthrough. He showed that a random Latin square, any size, likely has at least one transversal.
So that was a big crack in Euler's theory.
Exactly.
But how did this new research team go even further and actually disprove the whole conjecture?
They used a really powerful combination of techniques. One of the big ones is something called the semi-random method.
Semi-random, so not completely random.
Right. It's this clever approach often used in combinatorics. You're building a structure, but you're using a mix of randomness and deterministic choices.
Okay, so it's like guided randomness.
Exactly. It's like you're rolling the dice, but you're also kind of nudging the dice in a certain direction.
Got it. So in this case, they started with a model of a random Latin square.
Right.
So they're just like randomly filling in the cells, but still following that one symbol per row and column rule.
Precisely. And then they used some pretty advanced math to analyze that model and see if these random Latin squares could be decomposed into transversals.
So it's like they built a virtual lab to test out this centuries-old idea, right?
Yeah, exactly. A virtual lab to test out Euler's conjecture.
And what did their virtual lab show?
Well, their findings were pretty groundbreaking. They showed that not only do most Latin squares have at least one transversal, but almost all of them can be completely decomposed into transversals.
Wow, so Euler was wrong on a pretty big scale.
Pretty much, yeah. They showed that the number of Latin squares that can't be broken down this way is incredibly small, practically zero.
So they essentially flipped the whole idea on its head.
Yeah, pretty much.
But how do they actually prove something like that? It sounds insanely complex.
It is complex, but there's also a real elegance to how they did it. They broke the proof into 3 main parts. The first part involves something they call an absorption schematic.
Absorption schematic. Okay, that sounds intimidating. What's that all about?
Think of it like a blueprint. A blueprint for correcting little imperfections in the decomposition.
So it's like a plan for fixing things where the decomposition doesn't quite work out perfectly.
Exactly. The imperfections are these pairs of almost transversals, things that are super close to being real transversals, but need a tiny tweak.
Gotcha.
The absorption schematic helps them identify those spots and prepare for the adjustments they need to make.
Okay, I'm following so far.
Good, good.
So the first part of the proof figures out where these fixes need to happen.
Right.
But how did they actually make those fixes?
Well, they use these things called switchers.
Switchers.
Yeah, it's a simple idea, but really powerful. Basically, a switcher lets you swap elements between two of those almost transversals.
Oh, okay. So you're kind of doing a little surgery on the Latin square to make everything fit just right.
Exactly. It's like a tiny, precise surgery to transform those almost transversals into perfect ones.
That's a great analogy.
Yeah.
So first part, figure out where the surgery needs to happen. Second part, actually perform the surgery using these switchers.
That's it. That's a great way to think about it.
All right, I'm ready for part 3. What's the final stage of this proof?
Well, part 3 is all about tying up loose ends and making sure everything is perfectly balanced. Remember, we're trying to decompose the entire Latin square, every single cell. So this last stage is about making sure every cell is covered by a transversal and that all the symbols are distributed correctly.
So it's like the final quality check, making sure all the pieces of the puzzle fit perfectly, no gaps or mismatched colors.
Exactly.
All right, so to recap, they start with a careful plan using this absorption schematic.
Right.
They find the right tools, these switchers, and then they navigate the Latin square using these auxiliary graphs as maps.
Yeah, that's a great summary.
And finally, they do a final polish to make sure everything is perfect.
It's really quite an impressive piece of mathematical deduction.
It is.
Yeah,
That it all starts with just a grid of symbols.
Yeah.
But I'm sure our listeners are wondering, what's the point of all this? Is this just some abstract math puzzle, or does it have real-world applications?
Oh, that's an excellent question, and one we'll definitely dive into.
Okay, good, because I'm definitely curious.
The truth is, this ability to decompose Latin squares, it has some really interesting implications for a variety of fields.
Oh, cool.
Let's explore those after a quick break. Don't go anywhere.
All right, so we've set the stage, and now I want to get into the real-world implications of this breakthrough. You mentioned that this whole thing with decomposing Latin squares, it has applications in a bunch of different fields, right?
Absolutely, yeah.
Can you give us some examples? Like, how does this actually play out in practice?
Okay, well, let's start with cryptography,
Okay.
which is all about secure communication, right? Keeping information safe.
Right.
And that relies on some really intricate mathematical structures. And Latin squares, with those unique properties, they've been used in encryption algorithms for a while now.
So this research could potentially lead to even stronger encryption methods.
Exactly, yeah. This deeper understanding of transversals, it opens up new possibilities for, like, creating even more robust and sophisticated ways to protect sensitive information.
So, like, give me a concrete example of how that might work.
Okay, sure. Imagine you need to share a secret key with someone securely.
Okay, yeah.
You could use a Latin square that's been decomposed into transversals, where each transversal represents a fragment of the key.
Okay.
So only someone who knows how to put those transversals back together in the correct order can actually reconstruct the whole key.
Ah, that's clever. So, like, a puzzle that only the intended recipient can solve.
Yeah, exactly.
That's really cool.
Yeah.
So our passwords and online transactions, they could become even more secure thanks to this discovery.
Potentially, yeah. It's definitely an exciting avenue to explore.
Definitely. What other areas might benefit from this?
Well, another area is coding theory.
Okay.
Which is all about making sure data is transmitted reliably, even when there's noise or interference, you know?
Right, like when you're sending data over a wireless network or even like deep space communication.
Exactly. And you want to make sure that message gets through intact, even if some parts get garbled along the way.
Yeah, that makes sense. So how do Latin squares help with that?
Well, they play a crucial role in designing those error-correcting codes that make that reliable data transfer possible.
Okay.
And using Latin squares that can be decomposed into transversals, it lets us create codes that are more efficient and more resistant to errors.
So it's like they can handle more bumps in the road, so to speak.
Exactly, yeah. So you get faster and more reliable data transfer for everything from, streaming videos to scientific data from space probes.
So we've got secure communication and reliable data transfer. Those are pretty huge already. Any other areas we should be excited about?
Oh, absolutely. We can't forget about experimental design.
Okay.
In scientific research, it's super important to design experiments that minimize bias and maximize the information you can get from the data.
Right, so you're getting the most accurate results possible.
Exactly. And Latin squares are actually really helpful tools for creating balanced experimental design.
Oh, okay, I didn't realize that. Can you give me an example of how that works?
Sure. Imagine you're a scientist testing the effects of, say, different fertilizers on crop yield.
Okay.
And you have, let's say, 5 types of fertilizers and 5 plots of land.
All right.
You could arrange these in a 5 by 5 Latin square, where each row is a different fertilizer and each column is a different plot.
Got it.
This ensures that each fertilizer is tested on each plot, so you're minimizing the impact of variations in soil quality or other environmental factors.
That's really clever. It's like making sure everything gets a fair shot.
Exactly. And being able to decompose that Latin square into transversals gives researchers even more control and flexibility in how they structure their experiments.
So they can fine-tune things even further.
Yeah, which leads to more robust and reliable results. And that can have big implications for lots of scientific fields, from medicine to agriculture to material science.
Wow, the ripple effects of this seemingly abstract math are really far-reaching. But before we get too lost in the applications, I want to come back to the math itself for a bit.
Sure.
Can we unpack some of the technical details behind the proof a bit more? Like you mentioned this semi-random method and auxiliary graphs.
Yeah, of course.
Can you elaborate on those a little more, for those of us who aren't professional mathematicians?
Of course. So the semi-random method, it's this delicate balance between randomness and control. It's kind of like you're building something complex, but instead of placing each piece very deliberately, you let some randomness, like rolling a die, guide your choices. But you're not letting chance take over completely, right?
Right.
You're setting the parameters, making strategic decisions along the way to steer the process towards your goal.
So it's like guided self-assembly.
Yeah, that's a great way to put it. And in this case, the researchers are using it to construct those near transversals and the switchers. They start with a random Latin square, and then they use special algorithms to kind of like progressively refine it, making careful choices at each step to make sure they're getting closer to that complete decomposition.
So they're taming randomness, essentially, to achieve a specific goal.
Precisely. It's a really powerful technique.
That's fascinating. What about those auxiliary graphs? How do they fit into all of this?
Well, auxiliary graphs are like they're like a tool that helps you look at a problem from a different angle.
Okay.
You take this complex problem and you translate it into a different setting, sometimes a simpler one, where it might be easier to analyze.
So it's like instead of staring directly at the Latin square, they create these helper graphs to give them a new perspective.
Exactly. And in this case, they create these auxiliary graphs that capture the relationships between the transversals, the near transversals, and those switchers. And by looking at the properties of these graphs, they can figure out crucial things about the original Latin square, like whether those switchers exist and how many there are.
So it's like a map to help them navigate this complex maze.
Yeah, that's a great way to put it. The auxiliary graph is like a map that guides them through the randomness of the Latin square and helps them find those specific spots where they can make those little surgical adjustments.
It all sounds so incredibly intricate.
Yeah.
It's like they're using all these different tools from probability, graph theory, algorithms.
It is. It's a really clever combination of different mathematical techniques.
But I'm curious, are there any limitations to this research? Are there any questions left unanswered or areas where more exploration is needed?
Yeah, that's a great question. I mean, in math, there are always more questions to ask, right?
Right.
One thing is this research focuses on what we call asymptotic behavior.
Asymptotic. Okay, what's that mean?
It means it describes what happens when the Latin square gets really, really big, like infinitely large.
Ah, okay. So for those massive Latin squares, we know almost all of them can be decomposed this way.
Right.
But what about smaller ones? Like what if it's only 5 by 5 or something?
That's a good question, and it's actually one of the open questions that remains. This proof doesn't necessarily apply to smaller squares. It'd be interesting to see if there are any exceptions to this whole decomposition rule when you're dealing with, smaller sizes.
There's a chance that Euler might still be right about those special cases he identified.
It's possible, but honestly, pretty unlikely given how strong this new research is. Okay. Another thing that would be really interesting to explore is the computational complexity of actually finding these decompositions.
So, we know they exist, at least for most Latin squares.
Right.
But how hard is it to actually calculate them?
Exactly. That's a question that often comes up in combinatorics. Knowing something exists and being able to actually find it efficiently are two very different things.
That's a good point.
And finally, there's always the question of generalization. Can we take this breakthrough and apply it to other types of combinatorial structures beyond just Latin squares?
So potentially the implications of this research could go even further than we currently understand?
Exactly. It's really just the beginning of a whole new chapter in combinatorics. It's a really exciting time to be working in this field.
It sounds like it. All right, well, I think we've covered a lot of ground here,
We have, yeah.
but I feel like we've only just begun to explore the depths of this research paper. There's so much more to uncover. So I think we need to take another quick break here, and we'll come back to delve into the final act of this mathematical masterpiece. Stay with us. Okay, we're back and ready to tackle that final stage of the proof. We've talked about the absorption schematic, those clever little switchers, those powerful auxiliary hypergraphs. What's next in this mathematical journey?
Well, you could say this last part is all about bringing harmony and balance to the whole decomposition. We've set up the stage carefully, laid the groundwork, and now it's about making sure every single element, every cell in that Latin square finds its perfect spot.
So it's like, I don't know, the final arrangement of a flower bouquet, right? Making sure each flower adds to the overall beauty and balance.
That's a lovely analogy. And just like a good florist considers the color and shape of each flower, the researchers focus on three key things in this last part: covering, balancing, and partitioning.
Okay, let's break those down one by one. What do they mean by covering in this context?
Covering is pretty straightforward. It's about making sure every single cell in that Latin square is part of one of the transversals. Remember, we want a complete decomposition, no cell left out.
Right, we want that perfect tiling, those transversals like colorful tiles completely covering the Latin square.
Exactly. And a lot of the hard work has already been done in those earlier stages, right?
Yeah.
They use the absorption schematic, those switchers, the sparse, well-connected graphs, all to get us close to a perfect decomposition.
Right.
But there might still be a few stray cells, a few gaps in the tiling that need attention.
So they have to figure out how to weave those leftover cells into the existing transversals.
That's it. And to do that, they use a clever mix of random partitions and greedy algorithms.
Okay, remind me what those are and how they work here.
Imagine you have a ton of objects and you want to split them into smaller groups. A random partition is basically like shuffling those objects and randomly tossing them into different piles, trying to keep things roughly even.
So like dealing cards to a group of players, but randomly.
Exactly, and that's what the researchers do with those leftover cells. They use these random partitions to divide them into smaller, more manageable sets. This makes it easier to analyze them and figure out how to fit them into those existing transversals.
It's like breaking a big problem into smaller bite-sized pieces.
Yeah, exactly. And once they've got those smaller sets, they use greedy algorithms to figure out the best way to add those cells in. A greedy algorithm is kind of like always choosing the option that looks best right now without worrying too much about the bigger picture.
So taking the easiest route at each step.
Pretty much, yeah. So the greedy algorithm looks at each set of those leftover cells and tries to add them to transversals with as few changes as possible to the overall decomposition.
Like a careful game of Tetris, finding the best way to fit those last few pieces in.
Exactly. And by using random partitions and greedy algorithms together, they can efficiently cover all those remaining cells, making sure the entire Latin square is tiled perfectly.
Perfect. So all the cells are covered. What about this balancing step? What exactly needs balancing?
Balancing here is all about the symbols in the Latin square. Each symbol, remember, only appears once per row and once per column. And when we break down the square into those transversals, we want to make sure the symbols are spread out evenly across them.
So no transversal ends up with way too many of one symbol and not enough of others.
Right. We're aiming for a nice, even distribution, making sure each transversal reflects that balance of the original Latin square.
Like a well-balanced musical ensemble, each instrument adding its unique voice to the harmony.
That's a great way to put it. And to achieve this balance, the researchers get really clever, using those sparse, well-connected graphs again.
So those checkpoints, they're not just for navigating, they actually help with balancing too.
Exactly. They analyze how the symbols flow through those checkpoints, using those connections in the graph to move symbols around if needed.
Like they're directing traffic, making sure the symbols flow smoothly throughout the entire decomposition.
Precisely. They can spot places where a certain symbol is overrepresented and then use those connections to redirect them to transversals where they're needed more.
It's like a system of canals and locks, controlling the water flow to maintain a balanced level everywhere.
That's a great analogy. And by expertly managing those flows, they can get a really impressive balance in the symbol distribution across all the transversals.
Fantastic. So we've covered all the cells, we've balanced the symbols. What's this last step, partitioning, all about?
Partitioning is like the final touch, bringing everything into perfect harmony. We've been building up these transversals, these rainbow matchings, step by step. Now we want to organize them into neat groups, making sure each group is self-contained and contributes to that overall balance.
So like taking all those carefully arranged flowers and grouping them into beautiful bouquets, each one a little masterpiece on its own.
Exactly. To do this, they use something called parallel classes from the world of combinatorial designs. A parallel class is basically a set of objects, in this case our transversals, that don't overlap at all.
Oh, okay. So it's like separating a deck of cards into suits, right? Each suit has its own complete set of cards, no mixing between them.
Perfect example. And the researchers cleverly divide those transversals into these parallel classes, making sure each class has a balanced mix of symbols.
So each bouquet of transversals has a beautiful blend of colors, reflecting that overall balance of the Latin square.
Precisely. And by doing this, they complete that last step of the proof, showing that almost all Latin squares can be broken down into these beautifully balanced and organized collections of transversals.
This has been a mind-blowing deep dive. We started with just basic Latin squares, and now we've gone through this incredible journey of mathematical discovery.
It really shows how powerful math can be, right? And how these seemingly abstract concepts can have real-world applications that affect us all.
It's amazing how pure curiosity can lead to such practical breakthroughs. It makes you wonder what other mysteries and connections are out there waiting to be found.
That's the beauty of math. It's a constant adventure, and I can't wait to see what we uncover next.
Absolutely. Thank you for joining us on this incredible deep dive into the world of Latin squares. Until next time, keep those brains buzzing and keep exploring the wonders of the mathematical universe. All right, let's jump right in. Today, we're going to do a deep dive into Latin squares, and specifically this really fascinating paper by Bowtell and Montgomery.
Yeah.
You know, I think a lot of people remember Euler's conjecture about those rebellious 4n+2 Latin squares that supposedly couldn't be decomposed into transversals.
Right.
And this research kind of throws a wrench in that whole idea.
It really does.
And shows that most of these squares are actually incredibly structured.
Yeah, and what's really exciting here is that they don't just disprove Euler's conjecture for like a few specific cases. They actually prove that almost every Latin square, and we're talking a statistically significant majority, can be fully decomposed into transversals.
That's incredible.
Yeah.
It's like finding hidden order in what we thought was chaos.
Absolutely.
Now, for those who haven't encountered Latin squares in a while,
Sure.
Let's do a quick recap.
Yeah.
So a Latin square is basically an NXN grid where you have n different symbols, and each symbol appears
exactly once in each row and column.
exactly once in each row and column.
Yeah.
And then a transversal, just to remind everyone, is a selection of n cells from this grid where there are no repeated symbols.
Right.
And no repeated row or column positions.
Right, like a perfectly diverse sample from the grid.
Yeah, exactly.
Yeah.
So Euler's conjecture stated that Latin squares of order 4n+2 would be the odd ones out.
The oddballs.
They would refuse to have this nice decomposition into transversals.
Yeah.
And proving or disproving this has been
a
real challenge.
We had scratcher for mathematicians.
For a long time.
For a long time, yeah.
So what makes these 4n+2 Latin squares so tricky to work with?
One of the main challenges, I would say, is their rigidity.
Okay.
It's really difficult to make even small changes to a Latin square without breaking the rules.
Right.
It's kind of like a super strict Sudoku puzzle, you know? Right. And this rigidity makes it really hard to analyze their structure and see if they can even be decomposed.
So how did Bowtell and Montgomery overcome this rigidity hurdle?
Well, their breakthrough was to basically shift the problem from this world of Latin squares into a different world.
Okay.
They shifted it to the realm of graph theory.
Interesting. Okay.
And started representing Latin squares using what are called properly colored complete bipartite graph.
Hold on. Let's break that down a little bit.
Yeah,
What
yeah.
exactly
Yeah.
is a properly colored
Yeah.
complete bipartite graph?
Okay.
And how does it relate to a Latin square?
All right, so imagine you take the end symbols of your Latin square
Okay.
and you divide them into two groups,
Okay.
like two teams.
Got it.
A complete bipartite graph connects every member of one team to every member of the other team.
Okay.
But here's the catch. Each connection or edge has a color. Okay.
And no two edges meeting at the same point can have the same color.
Okay, I think I'm starting to visualize it.
Yeah.
So if we had, say, 5 symbols,
Right.
we'd have 2 teams of 5.
Yep.
And each symbol on one team would be connected to every symbol on the other team with a different colored line.
Exactly. And since it's a complete bipartite graph, every possible connection is made.
Right, right.
So if you have n symbols on each side,
Yeah.
you're going to need n colors total
Okay.
to make sure that no two edges meeting at the same symbol have the same color.
That makes sense. So where do the transversals from the Latin square fit into this colorful picture?
So each color in this graph represents a matching.
Okay.
A matching is basically a set of pairings
Yeah.
where no symbol is like double booked.
Okay.
And in this colored graph, a rainbow matching, which is a matching that uses all n colors, directly corresponds to a transversal in the original Latin square.
Ah, I see. It's like each color represents a category.
And a rainbow matching ensures we pick one representative from each category
Exactly.
without any overlap.
Precisely. And so this translation to graph theory was really key.
Okay.
Because instead of battling the rigidity of the Latin square directly,
Right.
they could now explore these colored graphs
Okay.
and figure out how likely they were
Yeah.
to have these special rainbow matchings.
So they just randomly generated a bunch of colored graphs and then tried to find rainbow matching.
No, that would be incredibly time consuming.
Right.
Their approach was much more strategic.
Okay.
They actually proved something very powerful,
Okay.
which is that a randomly generated Latin square of order n, which translates to a randomly colored complete bipartite graph in their setup,
Okay.
is actually very likely to have n disjoint rainbow matchings.
Meaning you could slice the whole graph into these perfectly diverse teams,
Exactly.
each representing a transversal.
Yeah.
That's pretty amazing.
It is.
But how did they actually prove that?
Well, their proof is broken down into 3 main parts.
Okay.
They call them parts A, B, and C.
Okay.
Part A sets up what they call an absorption schematic.
Okay, that sounds intriguing. Yeah. What is an absorption schematic?
Think of it as a blueprint for making strategic swaps later on.
Okay.
They use what are called auxiliary graphs,
Okay.
which are kind of like simplified versions of the full colored graph to help plan these swaps.
Okay.
And these auxiliary graphs help keep the number of potential swaps manageable
Okay.
and provide a framework for strategically maneuvering within the graph.
So it's like planning your moves in advance, knowing you might need to make corrections along the way
Exactly.
to achieve that perfect decomposition into transversals.
Exactly.
Okay, so part B.
Now, part B is where they bring those theoretical swap plans to life.
Right.
This part involves finding specific paths within the colored graph that correspond to those pre-planned swaps. And to do this, they use a really clever method called the rodal nibble.
Rodal nibble. That sounds interesting. What's the idea behind it?
So the rodal nibble is a very powerful technique for finding structures within graphs.
Okay.
It's not just about randomly picking edges.
Right.
It's a way to strategically select them in rounds to maximize your chances of finding a good solution without having to explore every single possibility.
So it's a way to navigate that huge space of potential paths.
Exactly.
And make smart choices, kind of like a guided search algorithm.
Exactly.
Okay.
So in each round of the rodal nibble,
Yeah.
they carefully select a subset of those pre-planned switching paths,
Okay.
which are represented by edges in those auxiliary graphs, and they add them to their kind of growing solution, making sure that the paths they select don't conflict with each other,
Okay.
meaning no shared vertices or colors.
Right.
And this process continues for several rounds.
Okay, I see how that would build up a structure piece by piece.
Yeah.
But do they actually end up with those perfect rainbow matchings?
So they get very close after running the rodal nibble.
Yeah.
The rodal nibble, when applied cleverly, like they do here, is remarkably effective.
Okay.
But it doesn't always guarantee a perfectly complete solution.
Okay.
Think of it like solving a jigsaw puzzle
Yeah.
and finding that you're missing just a couple of pieces.
So that's where part C comes in, the final cleanup and polishing.
Exactly. Part C is all about covering and balancing.
Okay.
They take that near solution provided by the rotal nibble
Yeah.
and use a combination of techniques to make sure all the vertices, those symbols from our Latin square,
Right.
and all the colors representing our transversals
Yeah.
are properly accounted for.
Okay.
Yeah.
Before we dive into the details of the proof, though,
Sure.
I'm kind of curious about how this whole problem
Yeah.
connects to the broader idea of resolvable designs.
That's a great question, and there's actually a really fascinating link.
Okay.
So a resolvable design is essentially a way to arrange objects into sets
Okay.
so that every object appears in exactly one set within each round or parallel class.
Okay.
Imagine like organizing a tournament
Oh, yeah.
where everyone plays in one match per round
Uh-huh.
and no one plays against the same opponent twice.
Right. Okay. I got it.
Yeah.
So how do Latin squares and transversals?
So you can think of a Latin square as a representation of a resolvable design.
Okay.
If you label the rows, columns, and symbols of the Latin square,
Uh-huh.
each cell now represents a unique combination, like
Okay.
a player, a round, and a match.
Right.
And a transversal would be a set of cells
Yeah.
that touches each row, column, and symbol exactly once,
Okay.
ensuring that every player is in one match per round.
Ah, I see. So decomposing a Latin square into transversals
Exactly.
is like finding a way to schedule that tournament
Right.
so that it follows all the rules of resolvable design.
Exactly. And this research actually has implications for a specific type of resolvable design called a Steiner triple system.
Steiner triple systems. Those ring a bell. Can you remind us what those are?
So a Steiner triple system is a design where every set
Uh-huh.
or block in this context
Okay.
contains exactly 3 elements.
Okay.
And these systems pop up in all sorts of areas of mathematics, like coding theory and network design.
Right.
Finding a perfect matching in a Steiner triple system, which is basically a set of blocks that covers every element exactly once,
Okay.
is very similar to finding transversals in Latin squares.
So by cracking this problem for Latin squares,
Yeah,
they're providing insights
precisely.
into these other areas of mathematics as well.
Exactly. They're building on the work of mathematicians who have studied these problems with Steiner triple systems.
Okay.
And they're really pushing the boundaries of what we know about matching in these structures.
Yeah.
And it really highlights the interconnectedness of different branches of mathematics.
Yeah. I love that this is getting really interesting. It seems like they're not just disproving a conjecture.
Right.
They're unveiling a whole new way of thinking
Yeah.
about these seemingly simple but surprisingly complex mathematical objects.
Exactly. It's a great example of how seemingly abstract mathematical research
Yeah.
can have these unexpected connections and applications in other fields.
But let's get back to the proof itself.
Sure.
We've talked about the big picture,
Yeah.
but I think it's worth understanding the mechanics of their approach.
Okay.
Starting with part A, that clever absorption schematic.
Right.
I'm curious about how they actually build this blueprint for making swaps.
Okay.
What are those auxiliary graphs like?
So their goal is to create a system where they can connect any 2 vertices in the graph.
Okay.
Remember, those represent our symbols
Right.
using a specific type of path that corresponds to a valid swap in the Latin square.
Okay.
But if they pre-planned every single possible swap, that would lead to a combinatorial explosion.
Right. Okay.
Way too many paths to handle.
It would be an organizational nightmare.
Exactly.
So they needed a way to simplify the problem
Right.
without losing the ability to make those crucial swaps.
Exactly. And so their solution was to create these auxiliary graphs
Okay.
that act like simplified maps
Uh-huh.
of specific regions within the full graph.
Okay.
So each auxiliary graph focuses on a subset of vertices,
Okay.
potential swaps.
Right.
And by carefully designing these auxiliary graphs and how they interconnect,
Yeah.
they ensure connectivity, the ability to get from any vertex to another
Okay.
without creating excessive complexity.
So it's like breaking down a large, intricate map
Yeah,
into smaller, more manageable regional maps
exactly.
that still allow you to navigate the entire territory.
That's a great analogy.
Okay, cool.
They strategically embed these smaller maps into the full graph
Mhm.
in a way that minimizes overlap between them, making sure that the paths they find in one auxiliary graph
Yeah.
don't interfere with the paths they need to find in others.
This all sounds very carefully orchestrated. It seems like they're finding a balance between
Yeah.
having enough paths to enable those strategic swaps and keeping the number of paths manageable.
That's exactly right. It's a very delicate balancing act.
Wow.
And their absorption schematic is essentially a set of instructions
Okay.
that tells them which paths in these auxiliary graphs they should prioritize when they move on to part B of the the realization stage, where they actually start finding those paths using the Rootle nibble.
Okay, so part A is all about setting the stage, carefully choosing those potential swaps based on these auxiliary graphs to give themselves the best chance of success when they start actually searching for paths.
Exactly.
This is really starting to highlight the level of ingenuity involved in this proof.
It really is quite clever. And, you know, the elegance of their approach is that it combines this deterministic structure, the Latin square, with probabilistic methods like the Rootle nibble to achieve their goal.
This interplay between randomness and structure is fascinating. It makes you wonder if other seemingly random systems
That's a great point.
might also have this hidden order waiting to be unlocked with the right mathematical tools.
It really challenges our intuitions about what's truly random and what might be governed by underlying patterns.
But before we get too philosophical,
I
think it's worth taking a closer look at how they use the Rootle nibble in part B to actually find those crucial switching paths. That's where the real magic happens.
Let's do it.
Let's delve into the mechanics of the Rootle nibble and see how they apply it to this problem. I'm ready to see how they bring this blueprint to life.
Okay. Welcome back. So let's explore part B of Bowtell and Montgomery's proof, where they use the Rootle nibble to actually find those critical switching paths within the colored graph that we've been talking about.
Okay, I'm really eager to dive into this Rootle nibble. It sounds like a very specialized tool.
It is.
From what I understand, it's not just randomly picking edges. It's a more sophisticated approach.
You're absolutely right. It's much more strategic than simple random selection. Imagine you're building a complex structure out of Lego bricks. But instead of having those step-by-step instructions, you're given a set of guidelines. And you need to choose the right pieces carefully to avoid getting stuck. The Rootle nibble kind of provides that strategic guidance.
I can see how that kind of strategic approach would be crucial when you're working with a structure that's as constrained as the Latin square.
Absolutely.
Where you can't just put any symbol anywhere.
Exactly. In this context, the Legos they're working with are those carefully selected potential swaps we talked about in part A. The ones that are represented by paths in those auxiliary graphs. And the structure that they're trying to build is a set of n disjoint rainbow matchings. Each of which corresponds to a transversal in the original Latin square.
So they're using the Rootle nibble to carefully piece together these small pre-planned swaps into these larger, more meaningful structures.
Exactly.
They will eventually give them those transversals.
Precisely. A key aspect of the Rootle nibble is that it operates in rounds. In each round, they don't try to solve the entire puzzle at once. Instead, they strategically select a subset of those Lego pieces, those potential swaps, that meet certain criteria.
What kind of criteria are we talking about? What makes a good swap in this context?
Well, they need to ensure that the swaps they select in each round don't conflict with each other. This means that the paths representing those swaps can't share any vertices or colors. They also want to choose swaps that maintain a good set of options for future rounds. It's kind of like thinking several moves ahead in a game of chess.
So they're not just optimizing for the current round, but they're also setting themselves up for success in the subsequent rounds.
Exactly.
It sounds like a delicate balancing act.
You're exactly right. And to guide their choices in each round, they use those properties that they build into the absorption schematic and the auxiliary graphs. It's like having a set of rules that help them navigate this complex puzzle.
So they're not relying on pure randomness. They're using the Rootle nibble in a very directed and controlled way. Guided by the groundwork they laid in part A.
Yes, the randomness comes in how they choose the swaps within those carefully defined guidelines. They run the Rootle nibble for a certain number of rounds. And at the end of this process, they have
a complete set of rainbow matchings.
Not quite complete, but very close. They end up with a set of almost complete rainbow matchings. It's a really remarkable achievement, getting so close to the solution using this probabilistic method.
Almost complete.
Right.
So there's still a bit of work left to do, I presume.
A little bit, yeah.
That's where part C comes into play.
Exactly. Think of it like this. The rodal nibble gets you 95% of the way there.
Okay.
But those last few pieces of the puzzle can be tricky.
Gotcha.
That's where part C, the covering and balancing phase, comes in.
Okay, so part C is where they find those missing puzzle pieces and make sure everything fits together perfectly to create those complete transversals. I'm really curious about how they handle that final stage.
It's a clever combination of techniques.
Okay.
They use some probabilistic arguments to ensure that the remaining edges and colors that they haven't used yet can be distributed in a way that completes those nearly perfect rainbow matchings into actual transversals. And they also need to make sure that all the vertices, which represent our symbols from the Latin square, are properly covered.
Right. Can't leave any symbols out.
Exactly. Can't leave anyone out of the party.
So if I understand correctly, part C is about taking that near solution provided by the rodal nibble and refining it to achieve a perfect decomposition into transversals.
Exactly.
Making sure every symbol has a place and every color is represented the right number of times.
Precisely.
This entire proof strategy is incredibly intricate. I'm really impressed.
It's a beautiful proof.
By how they managed to combine these different techniques, you know, graph theory, probabilistic methods, this absorption schematic, and then this final cleaning up phase. It's a real testament to the power of mathematical creativity.
It truly is. And what I find particularly fascinating is the implication this has for how we understand the interplay between randomness and structure.
I agree. It's very counterintuitive that a randomly generated Latin square, which seems inherently chaotic, could actually have this hidden, predictable structure that allows it to be decomposed into these neat, ordered transversals. It almost feels like finding patterns in static noise.
That's a great way to put it. It really challenges our assumptions about what we consider random and what might actually be governed by underlying patterns.
This raises some intriguing questions. What other systems that we perceive as random might actually possess this hidden order that can be revealed through clever mathematical techniques?
Exactly.
Could this approach be applied to problems in other fields, like analyzing complex networks or optimizing resource allocation?
Those are great questions, and they really blur the line between chaos and order. It seems like this research is opening up a whole new way of thinking about these kinds of problems. But for now, I think it's worth taking a closer look at how they actually use the rodal nibble in Part B to find those crucial switching paths. We've talked about the big picture. But I think it's really worth understanding the inner workings of this guided randomness.
Let's get into those details. So remember, the rodal nibble operates in rounds. In each round, they select a subset of those pre-planned switching paths. Those represented by edges in the auxiliary graphs, and add them to their solution.
Exactly.
And they have to be careful not to create conflicts by selecting paths that share vertices or colors.
It's like making sure none of your Lego pieces are trying to occupy the same space.
Exactly.
Now, to avoid conflicts and to ensure good options for future rounds, they use a probabilistic approach. Instead of deterministically choosing paths, they assign probabilities to each potential path based on its properties and its relationship to the paths they've already chosen.
So it's like they're weighting their choices based on how good a path is.
Exactly.
Both in terms of its immediate contribution to building the rainbow matchings and its potential impact on their ability to continue building successfully in future rounds.
Precisely. And they calibrate these probabilities very carefully, almost like a chemist, meticulously adjusting the concentrations of reactants in an experiment to ensure that with high probability, they will end up with a near solution after a specific number of rounds.
So there's an element of chance, but the odds are stacked in their favor.
Exactly.
Because they've so cleverly designed the rules of the game. They're really harnessing randomness in a very controlled and strategic way.
That's a great way to think about it. And this probabilistic approach actually works because of some powerful mathematical tools called concentration inequalities.
Concentration inequalities.
They sound intimidating.
They do a little bit.
But they're actually quite intuitive. Concentration inequalities basically tell us that under certain conditions, the behavior of a random process will tend to cluster around its expected value.
Okay.
So even though there's randomness involved,
Yeah.
the outcome is likely to be predictable
Okay.
within a certain range.
So in this context, it means that even though they're randomly selecting paths in each round,
Right.
the overall result of the rotal nibble is likely to be pretty close to what they expect.
Precisely.
Yeah.
And the specific concentration inequalities they use are tailored to the properties of the colored graphs that they're working with.
Okay.
They need to analyze how things like the degrees of the vertices, those represent the number of connections each symbol has,
Right.
and the distribution of colors affect how the rotal nibble behaves.
So it's not just blindly applying this technique. They're carefully analyzing how the rotal nibble interacts with the specific structure of their problem.
Yeah.
They're not just letting randomness run wild. They're keeping it on a tight leash.
That's right. And through this careful analysis and these probability calculations, they prove that after a certain number of rounds, the rotal nibble will, with very high probability, produce a set of almost complete rainbow matchings.
Almost complete, but not perfect.
Yeah.
That's why they need Part C to come in and take care of those remaining details.
Exactly. The rotal nibble gets them most of the way there, but they need those additional techniques to ensure that those final few missing edges and vertices are handled properly.
Okay.
It's almost like having a robot that can assemble most of a car.
Yeah.
But you still need a skilled mechanic to fine-tune the engine and make sure all the parts work together harmoniously.
This whole process is a remarkable blend of careful planning,
it is,
strategic randomness, and then that final touch of precision engineering. It makes you appreciate the ingenuity and the depth of thought that goes into solving these mathematical puzzles.
It really does. And what's particularly impressive is how this research builds on the work of other mathematicians who have explored similar problems with Steiner triple systems and other combinatorial structures. It's a great example of how mathematical progress is often built on this foundation of collaboration and shared knowledge.
It's like they're standing on the shoulders of giants.
Exactly.
Pushing the boundaries of what we know about randomness, structure, and the power of clever algorithms.
Absolutely.
Now, I'm really eager to hear about those final steps in Part C.
Okay.
And how they bring this whole intricate process to a satisfying conclusion.
Let's get to it.
Okay. So we've made it. We've gone through this whole absorption schematic thing. We've wandered through the probabilistic world of the rotal nibble.
It's been quite a journey.
It has been a journey. And now we're finally here. Part C of Bowtell and Montgomery's proof.
The grand finale.
This is where they take those almost perfect rainbow matchings and they turn those into complete, perfectly balanced transversals.
Exactly. This is it. The culmination of all our efforts.
Right, the ones we've been working so hard for.
This is where it all comes together.
So they call this phase, this Part C, covering and balancing.
Right.
And it's basically a two-pronged attack to make sure that every symbol is accounted for. And that every color is represented the correct number of times.
That's right. We got to cover all our bases.
So first, let's talk about those leftover vertices.
Okay.
The ones that the rotal nibble, might have missed.
Yeah, there might be a few stragglers.
Remember, those vertices represent our symbols from the original Latin square.
Right.
And we can't just leave any symbols unrepresented.
No, every symbol gets a place at the table.
It's like, everyone gets to play.
Exactly. Everyone's invited to the party.
So how do they handle these leftover vertices?
So remember those reserved edges we set aside way back at the beginning?
Oh, yeah.
The ones associated with that probability, BPT.
Right.
Well, this is where they come in.
Okay.
They use those reserved edges to create these small matching that specifically include those leftover vertices.
Oh, okay.
It's like a backup plan for those symbols that didn't get picked in the initial draft.
Like a targeted recruitment effort.
Exactly. Got to make sure every symbol is part of at least one matching.
Everyone gets on a team somehow.
Right.
Okay, so we've covered the vertices. Every symbol's got a place.
Right.
Now what about the colors?
So that's where the balancing part comes in.
Okay.
We need to make sure each color, which represents a transversal, remember, is complete and that it's balanced.
Yeah, like each team needs the right number of players from each category.
Exactly. They need to make sure each color appears the right number of times in that final set of matchings.
Okay, so how do they do that?
So to achieve this, they use a technique that involves strategically swapping edges between the matchings they've already created.
So they're like rearranging players between teams
Yeah,
to get that perfect balance.
right.
But how do they make sure these swaps don't mess up the structure?
Right. We don't want to undo all our hard work.
Yeah, the structure that they've already built so carefully.
Well, this is where those switchers we discussed earlier come in.
Oh, right.
Remember, those are the special paths.
Yeah, in the auxiliary graphs that
Yeah.
correspond to valid swaps in the Latin square.
Right, those pre-planned swaps.
Yeah. So they use these switchers to move edges between matchings, which redistributes the colors
Yes.
without messing up the overall structure.
It was like a trade.
Yeah.
But, in this mathematical sense,
Right.
you're making sure you're strengthening both teams.
Yeah, you're not making one team way too strong.
Right. Got to keep it balanced.
Okay, that's a great analogy.
So they analyze the color distribution in their current set of matchings, see if there are any imbalances.
Yeah.
And then they use those switchers to strategically move edges around,
Right.
essentially transferring colors.
Like a delicate balancing act.
Right.
You're carefully moving these pieces around to create this perfect harmony of colors.
Yeah, the very intricate process.
And once they've made all these adjustments,
then they have it.
they finally have it.
A complete decomposition of the Latin square into transversals.
Wow. So they did it. They actually pulled it off.
They did. It's quite remarkable.
It's incredible to think about how this, pretty abstract mathematical journey
Yeah,
has actually led to such concrete results
it has.
and challenged these long-held assumptions about Latin squares.
It really highlights the power of creative problem solving
Yeah.
and the beauty of mathematical ingenuity.
And the techniques they developed, the absorption schematic, the rodal nibble. It's amazing to think that this might actually be applicable to other areas.
Oh, absolutely.
In math and computer science, too.
Definitely, especially for problems that involve breaking down complex structures into these smaller balanced components.
I can see it being useful for like scheduling problems,
Yeah.
resource allocation, network design, even things like, analyzing social networks or designing algorithms.
It's really exciting to think about the possibilities.
It makes you wonder what other seemingly impossible problems might actually be solvable with this kind of approach.
It really opens up a whole new world of possibilities, right?
It does. It really does.
It suggests that even in systems that seem completely chaotic, there might be this hidden order just waiting to be discovered if we approach them with the right tools and a bit of creative thinking.
Absolutely.
Yeah.
This whole deep dive has been incredibly eye-opening for me.
Me too.
It showcases the elegance, the power of mathematical thinking,
Yeah.
and the surprising beauty that you can find in the most unexpected places.
It's a great reminder that the world of math is full of these mysteries just waiting to be uncovered.
It is.
And that even these seemingly simple objects like Latin squares can hold such profound insights.
It's been a pleasure exploring all of this with you today.
It's been great. I'm excited to see what other mathematical puzzles are out there waiting for us.
And what new discoveries are just around the corner.
Absolutely.
Welcome back to the Deep Dive. Today, we're going deep
Into Latin squares.
into the fascinating world of Latin squares and a recent breakthrough that's got the math community buzzing.
Yeah, this paper we're looking at tackles a problem that's been around, literally for centuries. And the solution is incredibly elegant. It combines probability and graph theory and combinatorics in a way that's just beautiful to see.
Yeah, for our listeners, let's start with a quick refresher on, what is a Latin square?
Sure.
It's an n by n grid, right? Where each row and column contains each of the n distinct symbols exactly once.
That's exactly it. Think Sudoku, but without the smaller 3x3 blocks.
Okay.
Each symbol appears exactly once in each row and each column.
Gotcha. And the big question here is about something called transversals.
Right.
Can you explain what those are?
Yeah, so a transversal in a Latin square is a selection of n cells, one from each row and each column, such that no two cells contain the same symbol.
Okay.
It's like a diagonal, but it doesn't have to be a straight line.
Okay, I'm visualizing it.
Yeah.
So what's this breakthrough all about?
So this paper proves that almost every Latin square can be completely decomposed into transversals. In other words, you can break down the entire Latin square into a set of these non-overlapping diagonals.
Wow, that's a pretty strong statement.
Yeah.
So how did they even begin to approach this problem?
Well, the proof builds on a lot of previous work, but one of the key starting points is a connection to Euler's conjecture from way back in the 18th century.
Euler, this mathematical giant.
Yeah.
What did he have to say about Latin squares?
So Euler was interested in whether certain types of Latin squares could even have transversals.
Okay.
He specifically looked at squares with an order that's 2 more than a multiple of 4, like a 6 by 6 square or a 10 by 10 square.
Okay, so specific sizes of squares.
Exactly.
And what did he conjecture?
He conjectured that these particular Latin squares could not have any transversals at all. It turned out he was wrong, but it took mathematicians over a century to disprove it completely.
A mathematical mystery that spanned over a century.
Yeah.
That's incredible. So this new paper goes even further than just saying Euler was wrong, right?
Absolutely. It shows that not only do these special Latin squares have transversals, but that almost all Latin squares can be entirely decomposed into them.
Wow.
It's a huge leap forward in our understanding of these structures.
Okay, so let's dive into the details of this proof. Where do they even begin?
So the key is a clever translation of the problem from the language of Latin squares into the language of graph theory.
Graph theory. So dots and lines come to the rescue.
Exactly. They represent a Latin square as a special kind of graph called a properly colored bipartite graph.
Now, I know graph means a network of nodes and edges.
Right.
But what makes it bipartite and properly colored?
Okay, so bipartite means the nodes can be divided into 2 sets.
Okay.
In this case, one set representing the rows of the Latin square and the other representing the columns.
Okay.
Each edge connects a row node to a column node representing a cell in the Latin square. Properly colored means that no 2 edges connected to the same node have the same color. The colors correspond to the symbols in the Latin square.
So it's like we're visualizing the Latin square as this network with like rows on one side, columns on the other.
Exactly.
And colored lines connecting them based on the symbols.
Precisely. And the beauty of this transformation is that a transversal in the Latin square now becomes a rainbow matching in the graph.
Rainbow matching. That sounds pretty. What exactly does it mean?
Yeah, a rainbow matching is a set of edges that connects every node on one side of the bipartite graph to a unique node on the other side, with no 2 edges sharing the same color.
So it's like a perfect pairing of rows and columns using all of the different colors.
Exactly. And decomposing the Latin square into transversals becomes equivalent to finding a set of these rainbow matchings that covers all the edges in the graph.
That's a brilliant way to reframe the problem.
Yeah.
But how do they actually go about finding these rainbow matchings?
So this is where the real magic of the proof comes in. They use a powerful technique called the semi-random method to construct these matchings step by step.
Semi-random method. So it's not just pure randomness.
Right. It's a delicate balancing act.
Okay.
They make random choices along the way, but they also carefully control the process to ensure that they can always fix any potential problems that might arise.
Sounds incredibly intricate.
Yeah.
Can you give us a bit more insight into how this semi-random method works?
It's a bit involved, but the basic idea is to build the rainbow matchings iteratively.
Okay.
At each step, they randomly select a set of edges, but they do so in a way that maintains certain properties of the graph.
Okay.
This allows them to keep track of the leftover edges and ensure that they can always find a way to incorporate them into a matching later on.
So they're kind of building the matchings piece by piece.
Yeah.
Always making sure they have enough flexibility to complete the puzzle.
Exactly. It's like solving a jigsaw puzzle where you can swap pieces around as you go, but you always have the full picture in mind.
This semi-random approach seems central to their proof.
Yeah.
But are there any other key concepts or techniques we should know about?
Yes, there are several. Another crucial element is the use of what they call switchers.
Switchers. Intriguing.
Yeah.
What are those exactly?
So a switcher is essentially a small subgraph, a mini network of nodes and edges that allows for local modifications of the rainbow matchings. Think of it like a railway junction.
Okay.
If a train needs to change tracks, the junction provides the flexibility to redirect it.
So the switchers provide a way to, like, reroute the flow of the matching if needed.
Exactly, and the brilliance of their approach is that they cleverly incorporate these switchers into the graph during the semi-random construction process.
Gotcha.
It's like planning ahead, knowing that you might need to make adjustments down the line.
It sounds like a brilliant combination of foresight and flexibility.
Yeah.
Now, you mentioned earlier that the proof is structured in 3 stages.
Right.
Can we dive into those now?
Absolutely. The 3 stages are the absorption schematic, the realization, and the covering and balancing. Okay. Each stage builds upon the previous one, leading to the final result.
Okay, let's start with the absorption schematic.
Okay.
What happens in this first stage?
So this is the planning phase.
Okay.
Remember those switchers? Well, in this stage, They carefully determine where those switchers need to be located within the graph.
Okay.
It's like creating a blueprint for a complex machine, figuring out where all the crucial components should go.
So it's all about setting the stage for success.
Precisely. They need to make sure they have enough switchers in the right places to handle any potential problems that might arise later on.
Mm-hmm.
This involves a lot of careful analysis of the graph structure and the properties they want to maintain throughout the construction process.
It sounds like a delicate balancing act,
Yeah,
ensuring they have enough switchers without overcomplicating the graph.
exactly. It's a fine line to walk, and their ability to find that balance is a testament to their deep understanding of the problem and the tools they're using.
Okay, so once they have this blueprint, this absorption schematic, what happens next?
That's where the realization stage comes in.
Okay.
Now they switch from planning to action.
Gotcha.
This is where they use the semi-random method we discussed earlier to actually find those switchers and start building those almost complete rainbow matchings.
So it's like taking that blueprint and turning it into a real, tangible structure.
Exactly, but it's not just a mindless assembly process.
Yeah.
They have to be very careful at each step to ensure that the choices they make align with the blueprint and maintain the desired properties of the graph.
It sounds incredibly intricate.
Yeah.
Navigating this space of random choices while staying true to the plan.
It is, and that's what makes this stage so fascinating.
Hmm.
It's a delicate dance between randomness and control, guided by their deep understanding of the problem and their clever use of probabilistic techniques.
So they're gradually building up these almost complete rainbow matchings,
Right.
using the switchers as safety nets along the way.
Exactly.
What happens in the final stage, the covering and balancing?
So this is where they bring it all together. They've laid the groundwork. They've built these almost perfect structures. And now they need to make those final adjustments to ensure that everything fits perfectly.
It sounds like the moment of truth.
It is. And this is where those carefully placed switchers really shine.
Okay.
They use them to swap edges, reroute paths, and fine-tune the matchings until they have a set of perfect rainbow matchings that completely decompose the original Latin square.
So it's like those final satisfying clicks as you snap those last few Lego pieces into place.
Precisely. And what's remarkable is that they can prove that this process works for almost every Latin square.
Hmm.
This means that the vast majority of Latin squares, no matter how large or complex, can be decomposed into these beautifully structured transversals.
This whole process is just mind-blowing.
Yeah.
It's like watching a master watchmaker carefully assembling all those tiny gears and springs,
Right.
knowing exactly how each piece fits into the larger mechanism.
That's a great analogy. The precision and ingenuity involved in this proof are truly remarkable, and the implications extend far beyond just Latin squares. This work has the potential to inspire new approaches to solving problems in other areas of math, and even in fields like computer science and engineering.
That's what makes fundamental research so exciting.
Yeah.
You never know where it might lead.
Exactly. And on that note, I think we've covered a lot of ground in this first part of our deep dive.
Yeah.
We've explored the basic concepts, set the stage for the proof, and highlighted some of the key techniques involved.
Yes, we've laid a solid foundation for understanding this remarkable breakthrough.
Right.
But there's still much more to uncover.
Absolutely.
We need to delve into the specifics of each stage of the proof and really appreciate the mathematical ingenuity at play.
I agree there are fascinating details to explore, including the specific probabilistic arguments, the clever use of graph theory, and the elegant way they handle those pesky leftover edges.
So join us as we continue our deep dive into this groundbreaking proof. We'll unravel the complexities, appreciate the beauty, and explore the broader implications of this remarkable mathematical achievement.
I'm excited to continue this journey.
Welcome back to the Deep Dive. We're continuing our exploration of this groundbreaking proof about decomposing Latin squares into transversals. And last time we set the stage explaining what Latin squares and transversals are,
Right.
and how this problem was cleverly translated into the realm of graph theory.
Yes, we saw how a Latin square can be represented as a properly colored bipartite graph,
Right.
and how the concept of a transversal morphs into a rainbow matching in this graph setting.
Right, and that's where the real fun begins. We left off talking about the semi-random method and these intriguing switchers.
Right.
Can we dig a little deeper into those now?
Absolutely. Let's start with the semi-random method.
Okay.
It's a powerful technique used in probabilistic combinatorics, and
Wow.
it's at the heart of how they construct those rainbow matchings.
Okay, remind me again, what's so semi about this randomness?
Yeah, so it's not just blindly making random choices.
Okay.
The process is carefully designed to create a balance between randomness and control.
Okay.
Imagine you're building a house of cards.
Right.
If you just randomly place cards, it'll likely collapse.
Yeah.
But if you strategically place some cards while allowing for some flexibility in others, you can create a more stable structure.
So it's like controlled chaos with a purpose.
Exactly. In this proof, they use the semi-random method to select edges for the rainbow matchings.
Right.
They don't try to find a complete matching all at once.
Right.
Instead, they gradually build it up in stages, making random choices at each step,
Got it.
but always ensuring that those choices don't lead to a dead end later on.
Sounds like they're walking a tightrope
Yeah.
between randomness and careful planning.
That's a great analogy, and that careful planning is where those switchers come in.
Okay.
They're like safety nets strategically placed along the tightrope.
I'm eager to learn more about these switchers. How do they work exactly?
Yeah, so a switcher is essentially a small subgraph,
Right.
a mini network of nodes and edges
Mm.
that allows for local modifications of the rainbow matchings.
Okay.
Think of it like a railway junction.
Okay.
If a train needs to change tracks, the junction provides the flexibility to redirect it.
So the switchers provide a way to like reroute the flow of the matching if needed.
Exactly. And the beauty of their approach is that they cleverly incorporate these switchers into the graph during the semi-random construction process.
Okay.
It's like planning ahead, knowing that you might need to make adjustments down the line.
It sounds like a brilliant combination of foresight and flexibility.
Yeah,
Now, you mentioned earlier that the proof is structured in 3 stages.
right.
Can we dive into those now?
Absolutely. So the 3 stages are the absorption schematic,
Oh.
the realization, and the covering and balancing.
Okay.
Each stage builds upon the previous one, leading to the final result.
Okay. Let's start with the absorption schematic.
Mhm.
What happens in this first stage?
So this is the planning phase. Remember those switchers?
Yeah.
Well, in this stage, they carefully determine where those switchers need to be located within the graph. It's like creating a blueprint for a complex machine, figuring out where all the crucial components should go.
So it's all about setting the stage for success.
Precisely. They need to make sure they have enough switchers in the right places to handle any potential problems that might arise later on.
Hmm.
This involves a lot of careful analysis of the graph structure and the properties they want to maintain throughout the construction process.
It sounds like a delicate balancing act,
Yeah,
ensuring they have enough switchers without overcomplicating the graph.
exactly. It's a fine line to walk, and their ability to find that balance is a testament to their deep understanding of the problem and the tools they're using.
Okay, so once they have this blueprint, this absorption schematic, what happens next?
That's where the realization stage comes in.
Okay.
Now they switch from planning to action. This is where they use the semi-random method we discussed earlier to actually find those switchers and start building those almost complete rainbow matchings.
So it's like taking that blueprint and turning it into a real tangible structure.
Exactly. But it's not just a mindless assembly process.
Okay.
They have to be very careful at each step to ensure that the choices they make align with the blueprint and maintain the desired properties of the graph.
It sounds incredibly intricate, navigating this space of random choices while staying true to the plan.
It is, and that's what makes the stage so fascinating.
Mm.
It's a delicate dance between randomness and control, guided by their deep understanding of the problem and their clever use of probabilistic techniques.
So they're gradually building up these almost complete rainbow matchings,
Right.
using the switchers as safety nets along the way.
Exactly.
What happens in the final stage, the covering and balancing?
So this is where they bring it all together. They've laid the groundwork, they've built these almost perfect structures, and now they need to make those final adjustments to ensure that everything fits perfectly.
It sounds like the moment of truth.
It is, and this is where those carefully placed switchers really shine.
Okay.
They use them to swap edges, reroute paths, and fine-tune the matchings until they have a set of perfect rainbow matchings that completely decompose the original Latin square.
So it's like those final satisfying clicks as you snap those last few Lego pieces into place.
Precisely, and what's remarkable is that they can prove that this process works for almost every Latin square. This means that the vast majority of Latin squares, no matter how large or complex, can be decomposed into these beautifully structured transversals.
This whole process is just mind-blowing.
Yeah, it truly is a beautiful example of mathematical ingenuity, and the implications of this proof go far beyond just Latin squares.
Right.
It has the potential to shed light on other areas of math and even inspire new applications in fields like computer science and engineering.
That's what makes fundamental research so exciting.
Yeah.
You never know where it might lead.
Exactly. And while the specific details of this proof might be complex,
Right.
the underlying concepts are surprisingly intuitive and elegant.
Hmm.
It's a testament to the power of human ingenuity and our ability to find order and structure in seemingly chaotic systems.
Well, I think we've covered a lot of ground in this second part of our deep dive.
Yeah, we've explored the semi-random method,
Right.
those ingenious switchers,
Yeah.
and the 3 stages of this remarkable proof.
And we've seen how these different mathematical tools and techniques come together to create a solution that's both beautiful and profound.
Absolutely.
But before we move on to the final part of our deep dive, I think it's worth taking a moment to appreciate the broader significance of this work.
Yeah.
This is not just about solving a puzzle.
Right.
It's about expanding our understanding of fundamental mathematical structures
Absolutely.
and pushing the boundaries of
Yeah.
what we know.
I couldn't agree more. This research reminds us that mathematics is a living, breathing subject full of surprises and hidden connections.
Yeah.
And who knows what other discoveries await us as we continue to explore the vast and intricate landscape of mathematical knowledge.
On that note of wonder and exploration, I think we're ready to move on to the final part of our deep dive.
Okay.
We'll delve into some of the finer details of the proof,
Sounds good.
explore its connections to other areas of math, and ponder its potential implications for the future.
I'm excited to continue this journey with you. Join us as we complete our deep dive into this groundbreaking proof and uncover the full extent of its mathematical brilliance.
Welcome back to the deep dive. We're in the final stretch of our exploration of this incredible proof about decomposing Latin squares into transversals. We've covered a lot of ground, from the basic definitions to the clever use of graph theory and the semi-random method.
And now it's time to put all the pieces together and really appreciate the intricate workings of each stage of this proof. Remember, we're trying to show that almost every Latin square can be broken down into these non-overlapping rainbow matchings.
Right, those colorful connections in the bipartite graph that represent transversals in the original Latin square.
Yeah.
So let's revisit the 3 stages of the proof. The absorption schematic, the realization, and the covering and balancing. We've touched on them broadly, but I'm eager to understand the specifics of what happens in each stage.
Absolutely. Each stage has its own unique role to play, and the way they build on each other is truly ingenious. Let's start with the absorption schematic, which is all about planning and preparation.
Okay, we talked about this being like creating a blueprint. Can you unpack that analogy a bit further?
Imagine you're an architect designing a complex building before you even start laying bricks. You need a detailed plan that specifies the location of every wall, window, and doorway. This plan ensures that everything fits together seamlessly and that the building is structurally sound.
So the absorption schematic is like the architectural plan for the rainbow matchings.
Precisely, in this stage, they're not actually finding the matchings, yet they're figuring out where those crucial switchers need to be located within the graph to ensure that they can handle any potential problems that might arise later on.
Right, those switchers, those little subgraphs that allow for local adjustment. So how do they determine the placement of these switchers? It sounds incredibly complex.
It is complex, and it involves a deep understanding of the graph structure and the properties they want to maintain throughout the construction process. They need to make sure they have enough switchers, but not so many that they overcomplicate the graph. It's a delicate balance.
So it's like making sure you have enough emergency exits in your building without compromising its design.
Exactly. They need to anticipate potential bottlenecks or conflicts and strategically place those switchers to provide the flexibility to resolve them.
It sounds like they're playing a game of mathematical chess, thinking several moves ahead.
That's a great way to put it. And the brilliance of this stage is that they can actually prove that such a schematic exists for almost every Latin square. This means that, in principle, they can always find a way to decompose the square into transversals, even if they don't know the exact matchings yet.
That's pretty amazing. They're essentially guaranteeing success before they even start building.
Exactly. The absorption schematic lays the foundation for the rest of the proof. It's a testament to their foresight and deep understanding of the problem.
Okay, so once they have this blueprint in hand, what happens in the realization stage?
This is where the action starts. They take that carefully crafted absorption schematic and use the semi-random method to actually find those switchers and start building those almost complete rainbow mashings.
So it's like the construction crew arrives and starts putting the plan into action.
Precisely, but remember, it's not a purely mechanical process. They still need to make careful choices at each step, guided by both the schematic and the principles of the semi-random method.
All right, that controlled randomness where they make choices that maintain certain properties of the graph.
Exactly. They're constantly balancing two competing forces. the randomness that allows them to explore a vast space of possibilities, and the control that ensures they don't veer off course.
It sounds like they're navigating a labyrinth, carefully choosing paths that lead them closer to the solution.
That's a great analogy, and as they navigate this labyrinth, they're gradually building up these almost complete rainbow matchings. These matchings might have a few gaps or mismatches, but they're getting closer and closer to the final goal.
So they're creating these intricate structures, piece by piece, guided by the blueprint and their clever use of randomness.
Exactly. And all the while, those strategically placed switchers are waiting in the wings, ready to be called upon to resolve any conflicts or connect those final missing pieces.
Okay, so they've laid the groundwork, they've built these almost perfect structures,
Yeah.
and they have their trusty switchers standing by what happens in the final stage, the covering and balancing.
This is where the magic truly happens.
Right.
They take those almost complete rainbow matchings and use the switchers to make those final adjustments, ensuring that every node and every color is perfectly accounted for.
It's like those final satisfying clicks as you snap those last few Lego pieces into place.
Precisely. And the way they use those switchers is incredibly ingenious. They can swap edges, reroute paths, and fine-tune the matchings until everything aligns perfectly.
So they're essentially ironing out any wrinkles and creating a flawlessly smooth surface.
Exactly. And the remarkable thing is that they can prove that this process always works no matter what random choices were made in the previous stage. They can always use those switchers to create a perfect set of rainbow matchings.
That's pretty incredible. It's like they have a mathematical guarantee of success.
Exactly. And that guarantee comes from the careful planning in the absorption schematic and the clever use of the semi-random method in the realization stage. It's a testament to the power of human ingenuity and our ability to find order and structure in seemingly chaotic systems.
This whole process is just mind-blowing. It's like watching a master chef combine seemingly disparate ingredients into a culinary masterpiece.
That's a great analogy. The way they blend probability graph theory and combinatorics is truly remarkable, and the result is not just a proof, it's a work of art.
I couldn't agree more. And what's even more impressive is that this proof works for almost every Latin square out there. It's a testament to the universality of these mathematical structures and the power of the techniques they've developed.
And the implications of this proof go far beyond just Latin squares. This work has the potential to inspire new approaches to solving problems in other areas of math, computer science, and even engineering.
It's a beautiful example of how fundamental research can have ripple effects far beyond its initial scope.
Exactly. And while the specific details of this proof might be complex, the underlying concepts are surprisingly intuitive and elegant. It's a testament to the power of human ingenuity and our ability to find order and structure in seemingly chaotic systems.
Well, I think we've done it. We've explored every nook and cranny of this incredible proof. We've seen how they transform the problem, how they plan their attack, how they build those intricate matchings, and how they use those clever switchers to ensure a perfect fit.
And along the way, we've glimpsed the beauty and power of mathematics. We've seen how abstract concepts can be brought to life, how randomness can be harnessed for creative ends, and how careful planning and ingenuity can lead to remarkable breakthroughs.
This deep dive has been a true adventure, and I hope our listeners have enjoyed the journey as much as we have.
And if this has sparked your curiosity, I encourage you to explore the source material further. There's a whole world of fascinating details waiting to be discovered.
Until next time, keep those minds curious and keep exploring the amazing world of knowledge. Welcome to the deep dive. We're diving into Latin squares and Euler's conjecture. We've got this paper. Almost every Latin square has a decomposition into transversals. Sounds like a real head scratcher.
It's a fascinating one. It really shows how you can use probability to solve these really tough combinatorial problems.
Yeah. Okay, so the paper starts off with this introduction, right? Talking about Euler's conjecture and, how it's connected to decomposing Latin squares into transversals.
Right, and they even mention how Euler himself built a pair of orthogonal Latin squares of order 10 back in the 18th century. Pretty impressive for the time.
Wow. Yeah, definitely before computers and all that.
Yeah.
And they connect that to, like, resolvable designs, too.
Exactly. They talk about how breaking down a Latin square of order n into transversals is basically the same as a resolvable n design, on n points with a block size of 3.
Yeah.
It's cool how it all ties together.
It is. Okay, so they also mention how this problem has been around for ages. like centuries, right?
Yeah, and there have been all sorts of partial results and conjectures along the way.
Okay, so then they get to page 2, and they lay out their main result. Theorem 1.1. Basically saying, as the order of a Latin square gets bigger, the chances of it having a decomposition into transversals gets closer and closer to 1. So basically, almost guaranteed, right?
Pretty much. It settles the question for large enough Latin squares. And get this, they even give a specific formula for that probability.
Okay, before we get too deep into that, can we just take a step back? I mean, just to make sure everyone's on the same page. What exactly are Latin squares and these transversals? And how do they connect to Euler's conjecture?
Of course. So imagine a grid, like a Sudoku puzzle, right? With n rows and n columns. A Latin square of order n is basically arranging n different symbols in that grid. But each symbol can only appear once per row and once per column.
Okay, so like a super organized arrangement of symbols.
Exactly. And then a transversal in that Latin square is like picking out n cells, one from each row, one from each column. But you can't have the same symbol twice. It's sort of like a diagonal, but it doesn't have to be perfectly straight.
Gotcha. So like representing the whole square with a diverse set of symbols.
Exactly. Now, Euler's conjecture, this was all about whether Latin squares had what we call orthogonal mates.
Okay.
Two Latin squares of the same order are orthogonal if, when you put them one on top of the other, you get one unique pairs of symbols. So like imagine two Sudoku grids, one on top of the other, and every cell has a unique combination.
That's a cool way to visualize it. So Euler thought some Latin squares, those with order n where n is congruent to 2 modulo 4, wouldn't have these orthogonal mates.
Right, and it turns out a Latin square has an orthogonal mate only if you can decompose it into transversals. So if you can prove almost all Latin squares can be decomposed that way, you're disproving Euler's conjecture for those larger orders.
Makes sense. So on page 3, they outline their proof strategy, right? And it seems like they're using a mix of probability and graph theory, something about finding these rainbow matchings in colored graphs.
They basically represent the Latin square as a complete bipartite graph. It's denoted K sub, n sub, with n vertices in each part, one for the rows and one for the columns of the Latin square. Each edge in this graph represents a cell in the square, and they color the edges with n colors for the n symbols.
So each edge is like a specific symbol in a specific spot in the Latin square.
Precisely. And finding a transversal in the Latin square means you're finding what's called a perfect rainbow matching in that colored graph. A perfect matching is just a set of edges that covers every vertex, and a rainbow matching is where no two edges have the same color.
Ah, so they're taking the problem and turning it into a question about finding these colorful connections in a network.
Exactly. And that lets them use all the tools of graph theory and probability. And then they introduce this idea of a relaxed decomposition, finding almost perfect rainbow matchings.
So like matchings that cover almost all the vertices.
Right. And they use something called absorption, which is basically setting aside some edges and vertices so they can fill in any gaps later to make a perfect decomposition.
Like a backup plan.
Yeah, they call those reserved structures switchers. They can use them to make small changes, swap out edges, reroute things.
Okay, so they have a plan for finding these near-perfect matchings, and then they're going to fix them up later. What's next?
On page 4, they outline the 3 main steps. First, find the switchers. Then connect them into paths. And finally, use those paths to carefully adjust that relaxed decomposition into a perfect one. And for all of this, they use something called the semi-random method, which is a mix of random and deterministic steps. They also use probabilistic tools like Chernoff bounds and the deletion method to analyze how likely certain subgraphs are to show up in their random colored graph.
This is getting pretty complex. Are there any specific math concepts we should keep in mind as we dig deeper into this proof?
Yeah, they use a bunch of really sophisticated techniques. For instance, they define all these variables like probabilities and proportions, and they use notation like much less than to show how they're related. It helps them control how those quantities change as the Latin square gets bigger. They also split up the vertices and colors into specific sets, each with a specific role.
Wow, so it's super structured and systematic.
It is. They really lay out their strategy clearly.
Well, I'm ready to dive into the proof itself. Let's start with part A, where they talk about finding these switchers, right?
Let's do it. Part A, starting on page 5, is where they set up that absorption strategy, and it's got a lot of cool combinatorial stuff going on. Welcome back to the deep dive. We're digging into how almost every Latin square can be decomposed into transversals, remember? Last time, we were about to get into part A of the proof, the absorption schematic.
Right, this is where they set up that whole plan for finding those almost perfect rainbow matchings and then using those switchers to fix them up. They start off with lemma 3.3, which looks pretty intense.
It is. But think of it like this. It's their way of guaranteeing they can make those corrections later on. They build this collection of switchers in a really specific way. And they break it down, the proof of lemma 3.3, into 4 parts. A.1 through A.4, tackling each part of this construction.
Let's break it down then, step by step. What's the point of A.1?
Okay, so 8.1 is all about setting up some ground rules. Remember how they divided the vertices of the graph into those sets? Subi sub, subi sub, subi sub, all those.
Right.
Well, they have to make sure each of those sets has roughly the number of vertices you'd expect. So they lay out those properties in lemma 4.1, and they use those probabilistic tools like Chernoff bounds to prove them. It's like before you build a house, you got to make sure the ground's level, right?
Makes sense. So they're just like double checking their foundation before they build anything fancy on top of it?
Exactly. And then in 8.2, they switch gears. Now they're focused on this auxiliary graph called QB sub. It's going to be a model for creating their switchers. This graph has to be kind of special, sparse, but also well-connected because they'll need to find paths between specific pairs of vertices later on.
Why is that connectivity so important?
Because they're going to use those paths to create switchers that can fix a bunch of different problems later. They have to be flexible. They prove that QZ sub actually exists with all the right properties in lemma 4.4. That one's a really nice example of how they're using combinatorics to build a structure with really specific features.
So they're not just throwing in edges randomly into this auxiliary graph. It's like they're designing it with a purpose.
Exactly. Then in 8.3, they use QB sub to show they can create those switchers they need. And they use a surprisingly small set of vertex pairs to do it. So they've got another auxiliary graph here, L subu sub, that helps them achieve this.
They really like working with these auxiliary graphs, huh?
Yeah, and for good reason. Think of them like little mini problems that help solve the bigger problem. In this case, L sub sabu sub helps show they can create a ton of flexibility with just a small number of switchers, which is a big deal for their whole strategy.
Clever. It's like they're finding shortcuts to make the construction more efficient.
Exactly. And to wrap up part A, they've got A.4. Here they add a few more pairs to their set I sub sub. This is to make sure certain conditions, some regularity conditions, are met. Those conditions are a bit technical, but they're really important for when they use that semi-random method later on.
So they're being super careful, making sure all the pieces are in place for the next step of the proof.
Right. They don't want anything falling apart later. So once they've built up that whole absorption schematic with lemma 3.3, they move on to part B. This is where it starts to get really exciting.
Okay, so part B is called realizing the absorption structure, which sounds a bit more hands-on than that abstract setup in part A.
It is. This is where they show that the plan they made in part A can actually be done within their random colored graph world. They need to find those subgraphs, M sub 1 sub through M sub sub, the ones that will eventually form their matching decomposition. They outline all the requirements for those in lemma 3.4.
So it's like in part A, they drew up blueprints, and now in part B, they're proving that the building can actually be made with the materials they have available.
Perfect analogy. And they rely on that semi-random method, again, to do this. Plus, they use the dilution method to estimate the likelihood of certain subgraphs showing up in that random graph.
So still lots of probability and combinatorics going on.
Oh yeah, they're always analyzing those chances of things happening randomly. And, like before, they break part B down into 3 smaller parts, B1, B.2, and B.3, each focusing on a different type of structure within that random graph.
Okay, let's look at those subparts then. What's B.1 all about?
In B1, they're working on finding edge disjoint matchings between the set subi sub and X subi sub, and they do this for every target matching has. They only use edges colored from set D sub 1 sub for this, which you might remember was one of those color sets they defined earlier.
So, starting to put together that matching decomposition piece by piece, using specific colors and vertex sets.
Yeah, like laying down the foundation for the rainbow matchings. Then, in B2, they shift to finding these small matchings. But this time, it's for each vertex, U, that's in set subi sub, but not in our subi sub. These matchings use colors from set D sub 2 sub and connect to vertices from set U subi sub.
It's like they're filling in all the gaps, making sure every vertex gets to be included in a matching.
Precisely. And every step has all these probabilistic arguments to make sure these structures actually appear in their random colored graph. It's not a sure thing, but they're showing it's very, very likely.
Okay, and what about B.3? What happens there?
B.3 is where they finally get to building those switching paths, the ones they'll use to fix everything up later. They use colors from set D sub 3 sub and vertices from set Z sub sub. It's all very intricate, but the main takeaway is they can actually find all these structures with the right properties, all within this seemingly random colored graph.
It's really amazing they're finding all this order in what we thought was just random.
Yeah, it's really showing how probability can help us uncover deeper structures in math. And with part B done, they move on to part C, the grand finale of their proof.
Okay, so they've got their plan from part A. They found all the pieces they need in part B. What's left for part C?
Part C is where they put it all together, finally building those perfect rainbow matchings. They start with those almost perfect matchings from Part B and use the switchers and paths to fine-tune them into a complete decomposition. It's like taking a rough diamond and polishing it into a perfect gem.
Nice. So part C is all about those meticulous adjustments.
You got it. And as you might expect, it's full of clever combinatorics and probability, too.
Okay, so here we are at part C. This is where they finally take those near-perfect rainbow matchings and polish them up, turn them into a complete decomposition of the colored graph.
It's the culmination of all their work from parts A and B. They've got their schematic, they've got the building blocks. Now it's time to assemble everything.
Right, and they broke down part C, which they handle in Lemma 3.5, into 4 steps, C.1 through C.4, each step refining that process a bit more.
Exactly. They start with C.1, where they're focused on covering any vertices that were left out of those matchings they built in Part B. The goal is to have every single vertex included in exactly one rainbow matching.
So it's like making sure every piece of the puzzle fits, right? No gaps.
Right. And they use edges from a specific set called E sub 1 sub to create new rainbow matchings. They label these Masubi sub 1 sub. They're really picky about which edges they use, making sure they use colors from set C subi sub 1 sub, and connect vertices from set R subi sub 1 sub.
Sounds pretty specific.
Yeah.
Why so much attention to detail?
It's all about that balance. Remember, not only does every vertex have to be covered, but each color has to appear in just one matching. They prove they can find these Masubi sub 1 sub matchings in Claim 34, and that claim also makes sure these new matchings don't mess up that balance they need later on.
Okay, so it's like strategic gap filling, making sure everything stays nice and organized.
Exactly. And that balancing act continues in C.2. This is where they focus on making sure the colors are distributed evenly across all the different families of matchings.
Families. Remind me what those are again.
Right. Earlier on, they divided their target matchings into these groups called families. Each family is like a subset of the matchings, and they have to make sure each family has the right number of edges of each color.
So like each team needs a good mix of players with different skills.
Exactly. They get this balance in C.2 by moving edges around between families, using some auxiliary matchings they call subi sub. They prove they can always find these with the right properties in Claim 35. And this claim guarantees that the edges end up where they need to be, keeping things nice and balanced.
So they've covered all those leftover vertices and made sure the colors are balanced between families. What's next?
Now, in C.3, they shift focus to balancing those vertex degrees within each family.
Vertex degrees.
Yeah, making sure that each vertex in a family is connected to the right number of edges. So no one vertex is hogging all the connections, they all get a fair share.
Like making sure everyone on the team gets to play their part.
Perfect analogy. They do this by, again, carefully moving edges around, this time using auxiliary paths that they label subi sub. They prove they can find these paths in Claim 36, which uses a graph theory argument to show those paths can connect vertices and balance the degrees just right.
So constantly tweaking things, making these little adjustments to get that perfect harmony within each family.
Exactly. Every move planned out, each step bringing them closer to that final goal of a perfect decomposition.
And C4, the final step.
This is the grand finale. They use the remaining edges from set E sub 4 C sub to create matchings that cover any colors they haven't used yet. This one is probably the trickiest part of the whole thing.
Why so tricky?
Because they have to cover those last colors without messing up the balance they worked so hard to create in the previous steps.
A real high wire act, so how do they manage it?
They divide up the edges and colors into really specific groups, and they use probability to show that they can always do that. They bring in some more of those auxiliary graphs we saw earlier and use a theorem from graph theory called Hall's matching theorem to prove they can find perfect matchings within these graphs.
Hall's matching theorem. Sounds familiar.
It's all about matchmaking, actually. Imagine you have two groups of people and you want to pair them up so everyone has a partner. This theorem gives you a condition that guarantees you can do that. Basically, for any subset of people in one group, the number of people they collectively know in the other group has to be at least as big as the size of that subset.
Okay, so like enough potential partners to go around.
Exactly. And the authors apply this theorem to their graphs to show that they can always find perfect matchings that take care of those leftover colors without messing anything else up.
Wow, so they're using a theorem about matchmaking to solve a problem about decomposing Latin squares. That's wild.
It just goes to show you different parts of math can be connected in some pretty amazing ways.
Absolutely. So they wrap up C.4, they've proven Lemma 3.5, they've shown they can refine those almost perfect matchings into a perfect decomposition.
Exactly. And that also proves their main result, Theorem 1.1. It shows that for almost all Latin squares, no matter how big they are, you can break them down into transversals. They've basically cracked a problem that's been around for centuries, and they did it with this incredible blend of probability, graph theory, and pure ingenuity.
It's been an amazing journey working through this proof. We've seen how they used all these different tools, probability, graph theory, combinatorics, to come up with this really elegant solution.
It really shows the power of creative mathematical thinking.
And for everyone listening, we hope this deep dive has inspired you to explore a little more of the amazing world of math, Latin squares, rainbow matchings, and all the surprising connections that lie at the heart of it all. Keep those brains buzzing, and we'll see you next time.